Hi, everyone. In this video, I'm going to discuss the concept of four momentum. So for momentum, we'll often just write as P, just like we did with momentum in the past. And we're going to define it to be the mass m times the four velocity. Now, it's important to note that the mass is taken to be a Lorentz scalar. Now, historically, there were people in the past who toyed with the idea of a relativistic mass, which changes with reference frame. It's important to note that if you come across this, that's not done really anymore, and it definitely will not be done in this class. So when I talk about mass, the way we're going to define this quantity is as a Lorentz scalar. So this does not depend on reference frame. So if we talk about the mass of a particle, it doesn't depend on the frame of reference that you're in. So if you think about this equation for not very long, hopefully it's clear that the way the four velocity transforms is going to be identical to the way the four momentum transforms, since they only differ by this scalar. So just like the four velocity was a four vector and transforms in our really nice way, our momentum is a four vector, and it's also going to have those same nice transformation properties. If you like, we can write this out by component, where we have some time component and three spatial components. And these again are just m times ux. Oh, excuse me, that should be time. M ux, m uy, and uc. So this is going to be our four momentum. We're going to have different names for different components of this four momentum. So the first is a little easier. So this is relativistic momentum. This is made up of the spatial parts of our four momentum. So we're just going to focus on our spatial components. So we have P sub x, which is m u sub x. And again, we can write this as mv sub x, sort of the normal velocity that you would measure, divided by the square root of 1 minus v squared. And then the same for y and z, where you just substitute out that x for y and z. And we'll often write this with an arrow over the top to remind us this is just our three vector. This is just the three spatial components. We will then take our time component to be our relativistic energy. We'll write that as E, capital E. So E equals our time component of the four momentum. Might seem a little strange. Why are we choosing this time component of momentum, which is sort of a weird thing? What does this suddenly have to do with energy? Well, it might be a little bit clearer if you recall. So again, our time component of our four momentum is just the mass times the time component of our four velocity, which is the mass divided by the square root of 1 minus v squared. Again, this isn't why is this an energy? This isn't very enlightening. Well, if we consider the slow limit, and again, slow, I just mean relative to the speed of light. So let's expand in a power series. So power series for small v. What does this look like? This looks like m plus 1/2 mv squared plus some higher order terms, which of course, if v is small, these higher order terms just get smaller and smaller. So really it's these first two terms that say, hey, this looks like an energy, because the m here, that's some rest energy. right? Or rest mass, that's the energy associated with a particle that's just sitting still. And then this next piece is the good old-fashioned kinetic energy. So this is going to motivate defining the time component of our 4 momentum as some relativistic energy. And then eventually we're going to see that really is going to make sense. And this is really going to be our energy. So with those definitions in mind, let's consider P dot P. Right? Again, the reason we like taking the dot product of 4 vectors is because you end up with a Lorentz scalar, so something that's invariant. So we can calculate this in a couple ways. So this, the relativistic, or excuse me, the 4 momentum is just m times the 4 velocity. If you recall, u dot u is just 1. Oh, sorry, that should be m squared. So this is just m squared, right? U dot u is 1, always. Doesn't matter what we're talking about. The 4 velocity squared is equal to 1. Okay, so that's kind of interesting. And this is good because I've already discussed the fact that the mass is a Lorentz scalar, so the mass just squared should still be a Lorentz scalar. So that's good. We also can think about P dot P in terms of its components, which we just defined. So pt squared minus, that should be a minus sign, not an equal sign, minus px squared minus py squared minus pz squared. That first term is just our relativistic energy squared. And then that second piece is just our 3 momentum squared, right? The magnitude of our 3 momentum squared. If we set these two equations equal to each other, what we're left with is m squared equals e squared minus our relativistic momentum squared. I'm going to box this a million times because this is an incredibly important and useful equation because it's relating our mass to energy and momentum. And you might not notice it right away, but this is just E equals mc squared in disguise, right? E equals mc squared is this equation for an object which is at rest. So for p equals 0, an object is at rest, and where we've restored the factors of c. In this video, like we'll almost always do in particle physics, we're setting the speed of light equal to 0. Right? You can see that if we make those adjustments, then that equation I boxed a million times is Einstein's famous E equals mc squared equation. So hopefully that will convince you that this is going to be a very important and very, very useful equation in particle physics. All right, so that's the 4 momentum. Thanks.